what is it going to be about? It's about object-oriented programming, but not in a classic way. I'm not going to teach you how to write Java code or C++ code or Python code. This is not the intention of this course. The main objective is to change your understanding of object-oriented programming. I assume that you already know how to write Java code. I assume that you understand encapsulation, polymorphism, inheritance, types, subtyping. All of these concepts I expect you to have already from your previous classes. At this class, I will try to convince you that what you've learned before is not perfect in all cases. Sometimes it may not be perfect. Sometimes the way you know how to write code is wrong. And that's my objective. Classic way of programming. The classic way of programming doesn't have objects. The classic way of programming is where you have operators, you have variables, and you uh, you allocate your code in procedures. This is how Linux kernel is written. This is how many software products are written in this world, in procedural way, where we reduce the complexity of the code by defining procedures. One procedure, another, just like we did with our parser in the beginning of the lecture. We just created 5 different procedures and we called them together parsing procedures or parsing functions. If you look at the Linux kernel, you will see thousands or tens of thousands of procedures, each calling each other. One procedure is calling another one, passing data as arguments. They don't encapsulate anything. They don't have objects which encapsulate some attributes. They're always passing data in their arguments. If you want to pass big chunk of data, then you create a struct, you create a more complex structure in memory, you put all the elements in there, and you pass a pointer to this structure, to another procedure. But still, from procedure to procedure, we move data. This is classic procedural programming, and this is what C language is doing. C++ introduced classes. They made it possible to create a class, put all the data in those attributes, and then let the functions, let the methods deal with these attributes. From now on, we don't need to give those methods the pointers to the structure, to the location of the data, because the data is inside the class. It was quite convenient. It was quite convenient for people who were not so happy about passing those pointers to many procedures. And one more interesting uh, message about object-oriented programming. Again, people continue to complain that there are many definitions of object-oriented programming, as many as there are books and papers. People didn't find the common ground. They didn't find a definition of what's going on. They knew that we deal with objects now. They knew that we deal with encapsulation. We encapsulate a number, for example, in the circle. We encapsulate the radius of the circle. But what's next? What is allowed to do next? What is not allowed? How should we design our code? How should we design our algorithms? We don't know. There was no clear definition of that. Nobody knew. Alan Kay on the conference about object-oriented programming, he said that uh, I made up the term object-oriented, which is true, but I can tell you I didn't have C++ in mind. It was a joke, obviously. The audience was laughing, but it's not only a joke. It is very much true. The C++ actually made a lot of troubles to object-oriented programming. I believe because it gave programmers a lot of features which do not belong to object-oriented programming. They did it because of the performance concern, I believe. They wanted to make C++ On one side, object-oriented. On another side, fast. And like I told you, Smalltalk was slow. Smalltalk is about 10 times slower than C. If you write your code in C in Smalltalk and you write the same algorithm in C, and we'll compare the performance, it will be 10 times approximately, but it's an order of magnitude slower. But C++, not. If you write code in C++ and you write code in C, then you can make them at the same speed. Of course, if you write code in C++ with a lot of objects there and you start using many objects, then your code will also get slower and slower and eventually will be even slower than Smalltalk. But if you don't do that and if you use objects not in a right way, but in a way that usually C++ programmers use those objects, then your performance will be just fine and you will be able to call yourself object-oriented programmer. That's what's happening. This is what Alan Kay is complaining about. This is what the joke is about. Haskell also said that they have some object orientation inside. Lua, JavaScript, Ruby, Java, Go, PHP 3 and later, Rust, Swift, and even our own language, which we created in 2016. All of these languages are object oriented to some extent. Remember that, because JavaScript, if you compare JavaScript with, for example, Go, you will see different understanding of what is an object and what you can and cannot do with an object. Languages are different. And if you compare Java, for example, with self, then self doesn't have classes, for example, and Java does have classes. They're different, but all of them call themselves object-oriented languages. This is yet another confirmation that we don't know what is object-oriented programming. We call everything object-oriented programming. What exactly is object-oriented? Not so many people know, or maybe nobody knows, including myself. The complexity grows. This is the biggest enemy of all us programmers, the complexity. The more complex is the code, the bigger the trouble. The more difficult to maintain, the more difficult to edit this code. Another guy says that we are in trouble because of this. The complexity of object-oriented code remains its primary drawback. I concluded this myself using the quotes of these people and using my own experience. I think this is the trouble, the complexity. We need to find a way how to reduce complexity of object graph, how to make objects smaller, how to make their compositions smaller. The complexity usually equals to size. If you have something big, then it is most probably going to be complex. You reduce the size, the complexity will go down. You make your object smaller, you win. You make your method smaller, you win. You make the hierarchy smaller, you win. You make your modules smaller, you win. You make your web services or databases or even the monolithic products smaller, you win by that. Reducing the size is the key recipe for success. How to reduce the size, how to get rid of complexity. This is what we're going to talk about. Another complaint. I'm just giving you one by one, getting closer to the current time. This guy says that reading an object-oriented code, you can't see the big picture. And it's often impossible to review all the small functions that call the function that you modified. This indeed is true. When you look at the code, you look at one object, you see that the call goes to another object and then goes to another object and you lose track of that spaghetti code very soon, especially if the objects are inheriting each other. The inheritance is one of the biggest root causes of high complexity. Okay, let me summarize the history part. We don't know anymore what exactly is object-oriented programming and whether it helps us write better code. It was introduced by Smalltalk as a solution, as a mean, as a tool to write better code. But in the end, we have it as a tool to write bad code. That's the story. That's the history of the last, what is it, 60 years of development of object-oriented concept. Current understanding of objects is not behavioral. We don't treat objects as something with its own behavior. We treat it as a storage of data, as a namespace for procedures, as anything, but not a behavioral component, a behavioral entity. What does it mean, behavioral? What does this word mean? We will see now. Bad designers, they expose many features outside. They just say, do whatever you want because it's good for programmers, right? I give all the abilities there. I let you do whatever you want. Delete, move, resize, check the size, all of that. This is wrong design. The good design limit, make abstractions smaller. And because of that, the complexity will go down. Again, remember that idea that abstraction is something that you define. You're responsible for that. Yes, about file, you can say many things. Yes, about students, we can say many things. But imagine me being a teacher, instead of looking at just a number, 38 people, I would just say you name by name, asking you questions. Who are you? Where are you from? That will just increase the complexity of the whole lecture. Instead of delivering you the material, I will get into a lot of details which are irrelevant. Check all of your objects uh, for this quality. When you give a name to the object, think about it. Do we have the same entity? They say an entity, you see? Entities, things. Do we have the same entity, the same thing in the world? Not necessarily in the real world, because the file exists in the real world. But here we can talk about certain things which exist just outside of the program, just outside of the code which we write. In general, we prefer to design our world inside our program as a hierarchy of abstractions. At the highest level of abstraction, we have application, the module, the mobile game, or the web service. And then it breaks down into smaller, and at the bottom, we have abstractions like square, distance. Those are the most primitive abstractions. They stay at the bottom level. I split object-oriented programming into two parts, something which is bad, something which is good. Why I think this way? Uh, because if you design it this way, if you make your objects alive and not anemic, you will make your code easier to modify, easier to extend, easier to maintain, easy to read. These are the characteristics of the code which are at the same time subjective as well. You can tell me that, no, I like this code on the left, and it's for me, for you, it's easier to read than the code on the right. It may be so. If you believe so and you want to stay with that belief, I can understand it. I mean, it will be, let's put it this way, it will be impossible for me to convince you otherwise with the help of metrics, with the help of numbers. It's it's only subjective, it's only the matter of taste. I even wrote a number of books which are called elegant objects. You see, elegant, it's quite emotional definition. I'm not saying faster objects. I'm not saying more or less complex or more complex objects. I'm saying elegant. I would be able even to say beautiful objects. So it's unmeasurable. Elegant. Who is elegant? Are you elegant? Am I elegant? Is it an elegant iPad? Is it an elegant pencil? Well, to somebody it's elegant. To some other people it's ugly. The same for objects. You should define for yourself what is elegant for you, what is beautiful for you, where is that beauty, and then stick to that definition. I suggest you my own definition of elegance. And on these lectures, I will keep pushing you with this definition, but understand that it's subjective. I'm just telling you, for example, how to, I don't know, how to dress up. And I'm going to tell you, the t-shirt, which is gray, super elegant. The t-shirt, which is white, it's ugly. Don't wear the white t-shirt. You may disagree, of course, because it's subjective. an object as a function. Some people say that the way we are trying to present objects, we, people who think like I think, is very close to functional programming. If we always try to represent objects as this way and keep all the functionality there and encapsulate the data and never allow anybody to take the data out, then the object will start looking, any object will start looking as a function. You call it, it works for you, returns back the result. That's it. So it's not anymore a storage of data, which usually objects are. Usually we think that objects are storages of data and then everything comes from there. But if they're not storages of data, if we never can take their data out, then they become functions. And this is good. Two students I have. One student in this chat, the first one, the second one, the second one. For example, Eugen. We have Eugen and Eugen. We have two people in the chat who are both called Eugen. They have the same name. They're different people. Their identities are different, definitely. Their state, name, the same Eugen. If I say, for example, to each of them, say your name out loud, one of them will say Eugen, another one will say Eugen, but they will do it in different voice, and their behavior is different. So they behave differently. Even though their names, their state is the same, identity is different, but behavior is the same. You need to understand the difference between these two, between these three things: identity, state, and behavior. We want our objects to be uh, to be clear about this about this segregation. I think that algorithms and algorithmic way of thinking is one of the key or maybe the main enemy of object-oriented thinking. If you want to think in an object way, then you should stop thinking in an algorithmic way, which is counterintuitive. It may be counterintuitive for most of you programmers because you are taught to think in algorithms and to solve problems algorithmically, especially uh, if you are doing if you were ever participated in in the competitions of programmers, let's say ICPC or LitCode or Code Forces, all of those places and organizations and platforms, they encourage you to think and to resolve algorithmic tasks. They give you some problem, they tell you that there is a set of data as an input, and you have to provide a set of data as an output. They don't tell you how you should organize it internally. They don't ask for any specific design. They don't care about that. They just care about taking the data and producing the data. To my knowledge, there is no competition in the world which would train or test programmers for their ability to think about the design. Well, let's say I want to know, do you have a cat, a pet, a dog at home or not? One way is to ask you, do you have a pet? And you will tell me yes or no. Boolean value. You will return true or false. Or another approach, I just go to your house and check it. I just open the door, get in, check it, and I will know, do you have a pet or not? So which way is better? Which way is more respectful to you? I think the answer is obvious. The same for the object. If I do this, this is extremely disrespectful. This is, I'm taking the data out of this guy, of this circle, and then I decide how to calculate the area of it. The circle knows the formula. The circle knows how to calculate the area. It's his responsibility, it's his domain, it's his responsibility to do that. I should not take the data out. I should not check the existence of the pet in the house. I should ask you, do you have a pet? The same for the object. And the more I do like that, the more I design my code like that, the more stupid the objects will become. If I, instead of asking you, do you have a pet, I will always go to your house, and in many other cases, I will continue to do the same. You will, in the beginning, you will be unhappy. You will try to resent. You will try to push back. But I will continue. I will continue doing like that. Instead of asking you, instead of letting you encapsulate any information, letting you know some secrets. Instead of that, for example, I will know your password to your email. Instead of asking you, did you get the email? I will just use your password, go to your email box and check your emails. I'm not going to ask you. I'm going to just check it myself. I can. I just have your password, for example, and I will demand that you give me your password, and then I'll do the same. I'll do the rest. The coupling. This is what a long time ago was introduced. Maybe I don't know, 60 years ago, it was introduced in software development. This dualism, this duality of these two principles. They said, the authors of this idea, they said that our design, all the elements of the design must be not coupled together, so they must not know too much about each other. When I deal with the circle, I should not know too much about what's inside the circle. I should only know that there is a method which is called area. I call this method, I get the number back. How it works inside, why it works this way, how this area is calculated, I don't want to know. The less I know, the better. The less I know, the less coupled I am with this object. Second point, the cohesion should be high. Cohesion means that everything that I need to do my job stays inside me. In order to do something, I possibly may need some other objects to help me. The less of these objects I need, well, I may need it, I will need them. So the less of them I need, the more I can do by myself. Not even the more I can do, but cohesion means that everything that I do internally actually is needed for the tasks I solve. Okay, there's a question coming from one of you. What is the difference between a single responsibility principle and cohesion? Single responsibility principle is less formal. It's more like a folklore principle. It's like a story. Like, hey guys, make it single. It's difficult to explain what is single exactly here. What does it mean, single responsibility principle? Like, how many responsibilities uh, an average class in Java has? It's hard to say that it's going to be single. It's going to be one responsibility. If you look at the real code, you will see that there are 10 responsibilities, 12 responsibilities, 20 responsibilities, sometimes even 100 responsibilities. So what exactly is a responsibility, and how to count them? It's impossible. That's why people criticize that, including myself. On my blog, you can find an article about single responsibility principle where I'm saying that this is just a simplification, even primitivization of this fundamental idea. This idea is fundamental. Cohesion, because there nobody says that should be one single responsibility. They just say your design should be as cohesive as you can. It's going to be 100 responsibilities. Maybe it's cohesive enough having 100 responsibilities, or maybe it's not cohesive enough if you have 2 responsibilities. But this letter single is very misleading, because it's not misleading, but very simplified approach. The question is, how cohesive is this class? Meaning that, isn't it a teacher which is teaching at the same time object-oriented programming and how to cook pizza and how to play tennis? It looks like it is. It looks like this guy is teaching too much. That this is it's not even single responsibility. There are many responsibilities at the same time. We should not do that. Instead, we make many separate small objects where each individual object will have 1, 2, 3, maybe 4 methods, maybe up to 4 methods, maybe up to 5, very small number of methods, but not like that. When you have utility class, you are encouraged by the name to add there as much as you can. Because it's a utility class, it is kind of supposed to be the place where you put all the methods which you don't know where to place. You just put them there, because they are procedures. They are global procedures. They are blocks of code available in global space. Why not to put them there? Eventually, you're going to have utility class with 100 methods, which absolutely not correlate to each other. They are not anyhow connected to each other. You probably know now, maybe not completely believe, maybe not completely feel it, that methods are static methods are not a good idea. We will get to that one more time, many more times during the course. Just stay with the information you got so far, which is static methods. They make code less cohesive, more tightly coupled, and eager. Three problems. Because subclasses are accessed by their data fields, they do not offer the benefit of encapsulation. There is no encapsulation. You don't encapsulate, you don't hide the data. You don't own the data anymore. The data is available to other classes, to other people. This is wrong. You may think, if you are a newbie programmer, you may think it's good that other classes will get direct access to your data and they can use the data. That's what the data is for, to be used. But this increases the level of coupling, which we discussed on previous lectures. Coupling, remember I told you about this word, that the two things in programming, if they know too much about each other, if they are connected to each other too much, then this is bad for the design in general. We need to design our code so that the coupling goes down. We have less coupling, we lose coupling, we just don't know too much about each other. Yeah. So up to now, until this point, I was on the same page with him. He's right until this line where he says that these classes should be replaced with classes with private fields. This looks like a solution for him and many other developers, many other programmers. These programmers believe that as long as you don't have the public modifier here and you replace the modifier with a private, and then you introduce the getters, which basically return what's inside, and that's all they do, then the problem is solved. But it's not really solved, in my opinion, and I will try to convince you that this is not really a solution, because we still have the same ability for the same classes to get the same data from the class point. In my understanding, because there's no clear answer, I didn't manage to find this in literature. People don't give exact answer. What is a getter? In my understanding, a getter is a method which, like correctly said by Andrei, is the method which doesn't have any, well, doesn't do anything else except returning the encapsulated attribute, which is what this method is doing. This one is doing some calculation, some data processing, some evaluation, some preparation about something else. Even though the name has the get prefix here and the get prefix here, they both look like getters syntactically. But the left one, a proper name, a better name would be calculate next number. That would be a proper, a better name, not a perfect name, but a better name. Because we're not only getting this, we're actually producing something new. We're using internal data in order to calculate some new information, some new data. A getter is not producing anything new. Getter only takes what's encapsulated and just let it fly out. I'm demonstrating you this in order to show how deeply this paradigm is engraved into the philosophy of object-oriented programming these days. Programming languages even encourage programmers to do that. instead of telling them that you should stop doing that, because later in this course, you will see that this is wrong. This is a terrible idea to have in your code in the first place. But Ruby says, that's good. We don't care. We actually give you the instrument to produce this bad code, to design your code like this. So make more getters. We believe it's right. We believe it's a good idea to have getters. By using getters and setters, you can remove a field and compute the value from other fields. Well, that's a good point, actually. Maybe I'm not entirely correct about no value of set of getters, because that's right. If you introduce getters, the code will compile everywhere. And then, for example, instead of X and Y, you decide to have some internal implementation different inside the point, but you still have get X and get Y. You still maintain get X and get Y, but internally you turn them from getters into something else. Let's say they will stop delivering just the value of the attribute, they will start generating the value. That's true. That is possible. So they play the role of some sort of a backup solution. You let your clients to couple with you, to connect with you too much, but you have a plan B. If you decide to change your internal implementation, then you can break those connections. And how? By letting them think that you still have X and Y, but internally you have something else. For those who don't know what is DTO, or maybe you didn't know the name for that pattern, you're definitely using this pattern. You're using these intermediate transfer objects. This is the data transfer objects, not like a normal object, but an object which is created temporary just to transfer some attributes, some data attributes from one place to another. In one place, we create such an object. It goes for just a few microseconds. It arrives to another place. In that place, they take out the pieces of it and drops the object, and it gets destroyed by the, for example, garbage collection. This is intermediate, poor guy who has no life on its own, who has no identity, who has no hope for being a proper object. It's just a poor mule who is transferring the data from one place to another. In my opinion, it's wrong in general to use this pattern. This is like a bad idea in object-oriented programming. We should try to stay away from it as much as possible. And here I see the question that, is it like view in the MVC pattern? View is more about, no, it's not view. View is a different thing. View is an active component where you inject some data and then you ask this component to behave somehow, to render itself to HTML, for example. View is an active thing. DTO is a completely passive thing. It's completely anemic model. We discussed this on the first lecture when I said this term, anemic. It's somebody who doesn't move. It's somebody who is totally passive. This is what DTO is. The DTO has no action inside. There is no side effect anywhere. You cannot give control to the DTO. You cannot tell DTO, do this for me. It's completely dumb object. It's completely stupid. No brain inside. It's only a holder of data, which is not how we should design our objects in object-oriented programming. Every object, as I told you in the first lecture, must be an abstraction, an active abstraction of something in the real world. If it's a book, if it's an abstraction of the book, then I should be able to ask this object to do something like the normal book can do in the real world. Encapsulation is most often achieved through information hiding. We know this already, that encapsulation is I'm introducing you now to the idea of encapsulation, which is a great idea in general, but let's see how it is supposed to be implemented and what we have in Java and in other programming languages. Information hiding. We want information to be hidden. We don't want objects to tell other objects too much about themselves. I keep repeating that. We want them to hide information. The less other objects know about your object, the better. The less access they have to your data, the better for the design in general. He's saying, he continues, the encapsulation information hiding is the process of hiding all the secrets. You see, I underline that. The secrets of an object that do not contribute to its essential characteristics. Essential characteristics. Let's say I'm a teacher and I have, let's say, I don't know, I like tea and I don't like coffee. This information is my secret. In order to teach you, this is the function I'm doing. This is my behavior, teaching. This information is not essential to the functionality which I provide. And I'm hiding this information from you. I'm not telling you that. Well, I told you now, but before I was hiding that like a secret. And I keep hiding a lot, which is not essential. But something, of course, some information, maybe I may disclose, but it's better to keep everything secret and only provide you the teaching functionality. Just talking, teaching, and keep everything else secret. The same your objects should do. If the object has to, for example, let's say, generate a random number. This is, you have an object which you ask, give me the next number, and it gives you the next number. It has the seed for that. It has maybe some other numbers inside, maybe some other prepared data in order to generate this pseudo number for you. But this is secret. It should be secret for you. You should not know how it does it. You just ask, give me the next random number. How it works internally, no idea. Separation of concerns. You must design what is important here and what is important there separately. And the better you separate those concerns, the less coupling you have between them, the better. They're just using a different term, but you already know the idea. Coupling is wrong. The more one object knows about another object, the worse, the bigger problems you will have for your design. We agree with all that. It's all pure truth, 100%, what is said here in this quote. Well, I agree. But when we go for the implementation, when we start implementing that, then we don't really have this information hiding with getters. Getters don't enforce information hiding. Getters only make an illusion for us that we do information hiding. We had an attribute, we said, oh, we make it private, we introduce a getter. You didn't do information hiding. You didn't do encapsulation. You just added a getter. If you have one object and there are getters, and there is data encapsulated there, we have attributes and they're private, and then we have getters, and there's another object. And this object, when looking at the first one, it should respect, meaning that it shouldn't try to get too much data out of the original object. But it's hard to do if all we have is getters. Is all you have in front of you is just an object with many, many getters, and this is how you're supposed to read that how to deal with this object. Let's say it's a book DTO. That's all I have. Get ID, get title, get author. Of course, I cannot respect anymore. I will take all of this data and then deal with this data. I will make a coupling. I will make a tight connection with this DTO. And then if tomorrow something else will arrive from the database, not the ID, not title, not author, but maybe a different set of data, also about the book, then there will be a trouble because I'm already connected too much. I'm already coupled to this structure of data. Keep in mind that every time you have a getter, every time you allow somebody to take data out of your object, you encourage the creation of such controllers, encourage the creation of such procedural code which stays outside of all the objects and orchestrates things. That's why I'm in general against the MVC pattern. I think it's a very bad idea, the MVC pattern, because of this word, C, because of the controller. The model is okay, more or less. The V is perfectly all right. The C is a terrible component. because it's a controller. Controller, it's a place which controls everything. It controls objects. Objects become anemic. Objects lose control, and the controller gains control. We don't want that to happen to our objects. One of the fundamental principles of object-oriented design is to combine data and behavior so that the basic elements of your system combine both together. This is often a good thing because these data and behavior manipulates them are tightly coupled. He wants the behavior, let's say the calculation of the pounds, be tightly coupled, so stay together with the data which is being used. I would actually suggest a different word here. Instead of tightly coupled, I would say that, but that's very close, that they should be more cohesive. Remember, we discussed that there is a coupling and cohesion. Coupling means that two things are married together. Cohesion means that whatever I need, I have. So if I have everything, I'm not going to get married to anyone. Let's move it to the social life. If a person has everything that that person needs, money, happiness, where to live, how to cook, how to dance, how to travel, everything, then the necessity for the coupling is lower. That's the idea. So cohesion of that person is higher, and that's why the necessity to couple with someone is lower. The same in object-oriented programming. If your object is more cohesive, then you will be less coupled to other objects. If internally you can do everything you need to do with the weight of the box, for example, then external objects, they will just come to you and say, do the service for me. Thank you very much. Bye-bye. But they will not get coupled with you. They will not get your data out. They will not know too much about you. They will not even try to know much about you. The same principle in life, the same principle in programming. Tight coupling is bad when they're married, they're coupled together, and low cohesion is also bad. When the cohesion of some person is like the person, for example, cannot cook, cannot work, doesn't have money, doesn't have place to live, he always or she always needs help. Then it's less cohesive person, and of course it's the trouble. Then there need to be many coupling with the parents, with the wife, with the friends, many couplings. The person will be tightly coupled. The same for objects. So what to do in case of integration with third-party libraries? You get to the third-party library, you ask to provide you something. The book is coming from there, which is called book DTO, but not anymore DTO. And then what this book has to know, what has to do, put this functionality into the book. Don't take the data out and then use the data in the controller, but let the book be smart enough to do the job for you, to do what you want it to do. That's the ultimate idea. Maybe it's not so easy to implement. Again, like I'm saying, most libraries are designed different. They will, for example, not allow you to do something, to do anything with the class they return, with the object they return. They just return you the book and it's already a DTO. So what should you do? You just use it. But if you design your own libraries, then you do it differently. Try to follow this principle of Martin Fowler, not only him. In the blog post, he explains this idea. He's not, to my knowledge, he's not inventing it, but explains what it means. Move the functionality into the object. You, for some reason, need some data from the object. Think about why do you need it? What was your original necessity to do that? Why did you want the data to come out of the object? Because of what? Because you want to use this data somewhere. So let the object do the work for you. Let it be of course, your objects may become larger in this case. That's what people sometimes complain about. They say, well, if I move my controller functionality to the object, then the object will be large. Now it's small, just 3 attributes, 3 getters, boom, the object is small. Yes, of course, if you move the controller functionality to the object will become larger. Obviously. Sometimes you will even get duplication of code. Your controller functionality will stay in one object and another object. Yes, you will have this problem. But these problems we're going to deal later. We're going to see how to deal with these problems later. These problems are less critical than comparing to the problems of anemic objects. Because with anemic objects, you just don't have object-oriented programming. That's it. There's nothing to talk about. You just have some garbage procedural code with some DTOs inside. It's just different story totally. There's nothing to, it's not possible to help you in this case anyhow. You're just on the basic level, level 0, no object-oriented programming. When you move the functionality, your controller functionality into objects and create methods which you tell, which you call in order to trigger some functionality, you're getting the first level of object-oriented programming. Now the question is how to optimize. Then the decorators come into play, then some proxy patterns, all of this stuff shows up. Many getters and setters, you don't have object-oriented design. That's exactly what I told you just a minute ago. If you have many getters and setters, you have anemic objects, you're just not doing object-oriented programming, period. It's a fundamental problem. It's bigger than performance problems. It's bigger than security problems. It's bigger than everything, in my opinion, because your code is a mess. It's difficult to maintain. First problem must be solved first. Remove anemic objects. Second recommendation from me. So first recommendation, remember, tell, don't ask. Move the functionality into objects. Second, get rid of the get prefix. It may help as well, a little bit. Instead of calling your methods get author and get title, just call them author and title. In this case, it will look a little bit better. It will technically work exactly the same. Technical implementation is exactly like it was before. But without the get prefix, you kind of pushing yourself towards making these methods not getters. You will be interested, you will not be interested, you will give yourself a permission in this case to put some side effect there. If you start calling them this, you will stop thinking in the terminology of getters. You will look at and will see why there is only one return statement in this method. The method is called properly title. So it shouldn't be a getter. It shouldn't just return. It should do something meaningful. And if you start thinking that way, this meaningful content of the methods will start showing up. You will just inevitably become designing them larger, and eventually you will stop making them literally one-to-one for your attributes. Because getters, they are supposed to stay one-on-one. One attribute, one getter. One attribute, one getter. If you call them this way, you will get out of this one-to-one paradigm. Let me read the question. What if the functionality of a variable in class can be used in many ways? So logic could become very complicated and class structure could become a mess. Yes, Artyom, it will become a mess. It will become larger. This problem we're going to deal with later. Of course, you will get code duplication sometimes. You will get complex class structure, but it's better than anemic class because all of this will be inside your class, all the complexity. How are we going to deal with this complexity? You solve this problem separately, but what is good, you will put all the necessary functionality of a class for the class into one place. If you do it first, when you're just a beginning, just a newbie, like a junior programmer, then your class will may get large and large. It will have a, I don't know, 500 lines of code and maybe 12 or 20 different methods. It's better. Such a class of 20 different methods which do different things is better than anemic class which is short and many controllers which use this class. Okay, what is the difference between a DTO and a hash table? A DTO pretends to be an object. A hash table doesn't do that. A DTO encourages you to think that this is an object and this is object-oriented programming. You will believe that you can do it with the configuration file, configuration DTO, and you can do it everywhere else. While this is a prohibited practice, it should be just Don't go nowhere. You should forget about doing that. You should forget about DTOs, forget about getters. But if you keep that class in your file, in your code base, then it's like a disease will spread over the code base all over. Because you will see that this is allowed in our code base. We can do that. We have one very good DTO with 50 getters. So why can't I do another DTO in another place since I already have it here? So my code base is already DTO friendly. So why can't I use it everywhere else? Make it a no-go, a completely um, unallowed practice. Final recommendation. If you really need to get access, if you really have to have DTO, make it with public fields, public attributes. In this case, you explicitly demonstrate that this is a data structure. It's not really an object, it's purely anemic data structure. If you want to have it anemic, make it clearly anemic. Don't pretend that this is an object. Don't pretend that, well, actually, we're an object-oriented. No, it's not object-oriented world anymore. It's just a DTO. In this case, make it public. Make them public. Make all attributes public. That I will understand. If I see that, I know, okay, the author knows what they're doing. They know that this is just a data structure or data transfer object, no object-oriented programming. Perfect. They admit it. I can live with that. Immutable classes are easier to design, implement, use. They're less prone to error and more secure. That's a general summarization of what do we get if we design all our classes with the final modifier for all attributes. If you disallow any setters, if you say, because setters is what you have, which is something which people usually have to enable mutability. If you stop using this bad idea, then your classes will be easier to design, less errors, and more secure. Inside the class, if you design your class internally as immutable or make your class immutable, you get readability and safer code. What is safer, we'll discuss in a minute. Why immutable means safer, and what exactly is safe in terms of object-oriented programming. Maybe you already know what means safe. This is called side effect free programming. Side effect free. I have no side effect because my objects are immutable. I get this guarantee not because my method is designed properly, but because the method cannot break my object, cannot change the state of my object. Not break, but change the state of my object. It's impossible to do. An object is supposed to be an abstraction which is self-sufficient. This is the whole idea of an object. The object is something that knows everything what to do and can do it by itself. If you have something like a manager or downloader or reader or writer, it means that the control of this entity, which is self-sufficient, is in your hands, in the hands of this guy, or who is the printer or writer or something else. The most probably interesting name is, like he says, manager or controller. Controller may be, in my opinion, even more powerful name than the manager. Controller is somebody who is in control, is somebody who is deciding what to do with the objects. Controller usually takes an object or a number of objects, reads the data from them or gets the data from them through getters, and then proceeds the data and then does something meaningful with the data, and then puts the data back into those objects. And that's why it's called controller, because it controls. Everything is in his hands. Why is bad? Because the majority of logic will be moved into the controller, and the objects will become anemic. They will become dumb. They will become stupid. They will become slow. They will become passive. They will be just sitting and waiting for something to happen. But the controller will be active. What do we have in the end, design-wise? We have large controllers. If you deal with MVC, if you develop web applications, you know the trouble of them. We have large controllers, very stupid models, which is DTOs,
and then the views. All the logic is concentrated in controllers. And it's difficult to test them, it's difficult to debug them, it's difficult to understand what they do, it's difficult to get rid of code duplication there, because all the logic is taken away from the objects, and now it's put into the controllers. That's the problem. We should do the opposite. We should make those controllers very thin, and this is in general is a good strategy for the design of web applications, even if you use model view controller. Try to have your controllers thin, small, as small as possible. The controller should just find the object and then ask that object to print itself to the view. That will be the ideal controller. But if you have that controllers, such small controllers, you will find out that you don't need controllers in general. Eventually, if you make your controllers smaller and smaller, you will get away from the model view controller design pattern. The MVC will be gone. It will be just models or objects and the views. And that will be a proper design. If you don't encapsulate anything, it's not a proper object. Something is wrong. If you encapsulate too many attributes, or if you encapsulate 0 attributes, it's a trouble. It's a wrong design. The readers, they also, this is their problem. Controllers, readers, managers, they provoke us to do tightly coupled design, because, like I said, because those procedures, they're not going to be polymorphic. They just stay there, and they're supposed to be the reader. You just implement it once. You implement the reader, which knows how to read from the input stream. That's it. That's your implementation. But it should be different. It should be different input streams. The input streams must know how to read. This is their job. The input stream has to know everything about itself, how to read, how to process the data, how to understand whether it's the end of the stream or not, everything in the object. You may say that the object will be larger, and I will answer yes. The input stream will become larger in this case, definitely. If you get rid of those managers, controllers, and everything, your objects will become larger in size. But that's a different problem, a separate problem, and a smaller problem than the problem of tightly coupled those readers and managers and controllers, which look like a help for us. Let's go next. Controller. Look at the controller. On the left, you see a quite typical controller in Java when we implement web interfaces or just RESTful interfaces, RESTful API. You see that there's a controller with the clear name controller with the ER in the end, and two methods. The first one is for the index page. The second one is for the update page. I think you understand the design. When the index, it's the HTTP request comes in both cases, and we return something like the HTML pages or something like that. Again, it's not a good design because, like I said, the functionality will stay in those blocks in those procedures, and there will be no actually objects. If you start designing like this, you will see no place for objects in this case. You will ask yourself a question: where do I create objects and what for? I already have the two scripts. Now all I need is data in order to generate the index page, in order to generate the HTTP response. I don't need objects anymore, right? That's just end of design. The design is done. But then you have Java, so you start thinking, okay, but you have objects, so you need to put your code somewhere, and where it's going to be. Well, let's create a supplementary object which will help us to, I don't know, maybe render the HTML page, or maybe to hold some data. You start inventing where to put the objects. This is what I was doing for many years before I started thinking about object orientation. It was always the question where the objects, what the objects are for. And I was using objects mostly in order to just make my files smaller. Because I cannot put all the features and all the functions and all the algorithms into one large file, but I wanted to. That was my just obvious uh, desire in this case. All I needed just many scripts which process the data. Like here, I already started. Those are two scripts already in place. They're annotated. There's some name, controller, and then I need the processing, more scripts. So I was using objects, of course, but only as holders of procedures. Let's take a look at the right example, which is way better. Here we have two entities, two abstractions, which are the pages which we're going to generate, which are going to be active components. Now they're not scripts anymore, they are pages. And if you want those pages to act for you, to behave for you, then you tell them what to do. You tell them through the methods, of course. You tell them through the methods process, the method process, which are identical or very similar to those methods. Of course, we do not reinvent the whole thing. Of course, the request is coming in and the response is coming out, but now we have two separated entities, which are abstractions, I think good abstractions, of two elements of the design. We have index page, we have update page. And then we can combine them together into a new entity, a larger abstraction, which is, let's call them all pages. And these all pages will also implement the method process. And when the request is coming to this method, the all pages will decide which one to go for, this one or that one. It's going to be like a dispatcher, like a router, but it's not called a router, it's called all pages. Maybe for you it's a subtle difference because just a name difference, but it's a serious difference, just design-wise. Now we deal with the larger abstraction. We had two abstractions on the lower level, which is one page, another page, and then the larger abstraction, which is the aggregation of two abstractions. The age supposed to know whether it is valid or it's not valid. We are supposed to say, are you valid or not? Maybe even better, instead of saying, are you valid or not, we are supposed to deal with the age or with the user or with the person. And then if validation is not passed, we should be getting an exception. This is the right in general approach to designing objects which are supposed to be validated. You don't ask whether they are okay or not. You just deal with them, assuming that they are valid, assuming that everything is fine. And then when something goes wrong, they will throw an exception. They will tell you, okay, now I'm not allowing you to do that. I'm not allowing you to deduct the money from me because my balance is negative. But you don't check in the beginning. Is your balance positive? Is it allowed to deal with you? You don't put the validation functionality outside of the object because it belongs to the object. The object has to know everything about validation, not some entity which is outside of the object. If you use the design on the left, this one, you know you are in charge. You are the manager. You are the controller. You always need to remember when and how I validate who. And these people, the age, for example, they become stupid and stupid and stupid, dumber and dumber, passive and passive. You will worry more and more. You will have many validators in your controllers. Your controller will grow big because you need to validate this, you need to remember to validate that, you need to remember to check that. All those checkers and validators, it will make your controllers larger. And objects, they will stay empty with no functionality. We do it otherwise. We do it a different way. We put all this functionality into those objects. They will validate themselves. And how do you achieve that? You don't use the name validator. Start questioning your class names. And when the class name is ER, validator, reader, printer, you will see that there is no such entity in the real world which your reader or writer or validator is an abstraction of. The validator, what does it abstract? What does it represent? Nothing, because it's just a collection of scripts. It doesn't represent a real thing. Age is a real thing. Age is a real entity in the real world. We got it from there. It exists there. The age, it's a concept in the real world. And because of that, we have an abstraction in the code which represents the real age. But the validator, it doesn't exist anywhere. We just made it up. It's just a holder for our procedures, for scripts. We place those scripts there and call it a class. Don't do that. Every time you say it with an ER, you're doing it wrong. So the functionality may be either in the class. I'm just summarizing my ideas, which I just explained, which I just presented. You put the functionality either into the class or into the decorator, which makes your class more functional. Another decorator, more functionality. Another decorator, more functionality. But when this creature is coming to me as a consumer of that, I don't know about all those layers. I just deal with an object. I just ask, could you please do something for me? And then multiple layers of decorations or whatever happens there. I don't know about that. And I don't need to know. I don't need to remember that I need the encoder, and then I need the checker, and then a validator, and then something else, the printer. All that happens in the entity which flies to me in an object. We, together with a few students from another university in Russia last year, we did the research. We were interested to know whether these ER suffixes actually affect the quality of design. And we were measuring the quality of design by complexity. We know that the more complex is the class, the worst is the design of it. If the class is simple, then naturally the design is better. The complexity is directly connected with the quality of design. This is a well-known fact. That was our assumption. What if we compare average complexity of classes which are normal classes and the average complexity of classes which are ER controllers, managers, controllers, all that stuff? And you see what we found. We found out, and we analyzed 13,000 Java classes from 212 source code open source repositories. We grouped them into three separate groups. We got ER classes, we got utils classes, those are suffixes, and we got all other classes. And this is the complexity. You see the blue line is the average is the sorry, it's that's the average complexity of is the average value of the, for example, COCO is the cognitive complexity metric. All other classes are 3 times less complex than these two guys, which in my opinion kind of proves the point. It demonstrates that when people design these utility classes or manager classes, they make those classes 3 times more complex than normal classes. You should design your software the way that every time you hit the problem, you raise an exception. If it's object-oriented programming, if it's something else, you crash, you terminate your execution. You don't tolerate any errors, any problematic situations. And then he says, more and more errors will fail fast if you follow this principle, if you follow this idea and you do that kind of design. You will get many errors. Of course, your application will be very fragile. It will fail here and there. It will be very hard to use it. You touch any button, it just crashes and shows you the errors, the stack trace. But you will see, when the time comes, the cost of debugging decrease and the quality of your system will improve. That's counterintuitive, but this is what will happen. You will get more troubles, more bug reports, and you will fix them. You will fix those bugs. Well, of course, introducing tests for that. You will increase the coverage, the test coverage. You will add more and more tests, automated tests, and the bugs will be fixed. The bugs will not be hidden. The bugs will not be undetected. The system will be very fragile in the beginning, but eventually it will become way more stable comparing to the system which was following the principle of fail safe. Why returning null is a bad idea? Because you postpone the problem for later. You will return null, and somebody later will try to deal with this name of the employee, and it will crash. But that crash will not understand why the crash happens. Let's say I use your function and I do n equals to name of employee 42. And then I say n dot length. Here we will see NPE, null pointer exception. What I'm going to see in the stack trace? The stack trace will tell me null pointer exception. It's not going to tell me that the user is not found. It's going to be null pointer exception. I will get here to this line from the stack trace. I will look at that and see why the hell it's null. Why the name of the user is null? Well, I will have to go backward. I will have to find the place where n is assigned by this function, and then go to this function and try to understand why null is returned. But in some functions, they even return null in many places. It will be very hard for me to debug this situation because I have no information in the stack trace about the real root cause of the problem. I don't have the message that the user is not found. I have null pointer exception. Or if you deal with the C++, for example, you're going to have segmentation fault. And segmentation fault is even harder to debug. Who knows where it happens? Who knows why? So you basically postpone the trouble to later. You're doing a bad favor to your customers when you're returning null. And you have to do that. You have to deal with null every time it's coming to you. This is the indicator of a bad design. If you are checking for null in your code, it means that the design is wrong. But sometimes you deal with third-party libraries, which actually return null sometimes as an indicator of trouble or indicator of an absence of data, and you have to check for null. I just gave you a few options how to do it more or less correctly. Remember we talked about immutability when I told you that all objects must be immutable. Null is what you have when your objects are not immutable. Let's take a look at this example. This object is not immutable. It has a setter, and this is how you deal with this object. First of all, you create an instance of this class, and then you set the name of this class. This is a bad design. You don't do that. This is wrong. Why? Because in this, after this line, the object is in the state which is undefined. You have null there, which means we don't know what's there. We may potentially have a problem if we try to access the name. If you call some method of this function, of this object, then the object will start working with its internal attributes and it will crash. Why? Nobody knows. The reason, you didn't initialize your object correctly. You just created a broken object with incomplete state. So that's why you never make mutable objects. All your attributes must be final, and all of them must be initialized. You never do that. This is a horrible design. When you see that, you must know that the code you deal with is written by somebody who is not as good a programmer as you might expect. My point is that you don't store null. You just don't do it. Period. This is not something that we ever do in proper object-oriented programming. Why? Again, the same reason. We don't want to plant a bomb for future customers. When you make it like this, you're begging for trouble. You're just giving other lines of code the object which is a troublemaker for no reason. It's not like the fake entity, which is also a troublemaker, but with a reason. The fake employee knows why it fails. There's a reason for that. Here, it's just a broken object, which may crash at any moment of time. It will be very difficult to understand why it crashes. And the answer is easy, because you designed it wrong, because you made it incomplete by design. You gave the possibility to its users to instantiate it with an incomplete state. And this is state, remember? Every object has state, identity, and behavior. We discussed that. This is the behavior. Well, in this case, it's kind of defective behavior, but still a behavior. And this is the state. Now, a philosophy of that. Imagine we talk about objects in general, what they are. They are abstractions of real world entities, just like we discussed on the first lecture. An employee in your code is an abstraction of a real employee in the real world. When you deal with your objects, you should expect their behavior to be similar to the things that they abstract. If the employee in the real world has a salary, then your object has a salary. If the employee in the real world can be fired, then your object can be fired. You should mimic the behavior of what's happening in the real world in your design space. This is why null reference is a billion-dollar mistake. This is what we started from this lecture. Because the reference cannot be null. If I reference to an object, then I expect there to be an object. If the employee is on the line, I talk to the employee. But null we have everywhere, in Kotlin, in Java, in Python, in JavaScript, everywhere. All object-oriented programming languages, they have this concept of null. Unfortunately, it seems that people cannot live without that. It seems that it's so deep inside our mentality of us programmers. I suggest you to get rid of that concept. Don't send null, don't return null, don't store null. Just forget this keyword. Imagine you don't have it in your application. And that you will see that your code will become better and better and better. Because you will not have these validations, you will start respecting your objects. You will know that if there is a variable which refers to an object, then you can easily, safely, without any hesitant, without any hesitance, call the method of this variable, and there will be a return. There will be no null pointer exception. But people, when they deal with fail-safe design, they're always scared of touching the objects because they know that there could be null, there could be zero. And they need to check, double check, check again. And when they run the application, then we get null pointer exception and we start debugging. One restriction, one thing to mention, of course, we have to say that, is the performance. Performance, of course, will be higher if you use null references. Because throwing an exception is more expensive, and because returning the list is more expensive. If you really deal with something super fast and super high load, then you might consider returning null. But
you do it in exceptional situations. You do it only when the performance is a critical factor and you absolutely must, in this particular space, in this particular line of code, make sure that you don't do anything redundant. That will happen maybe once in your lifetime, maybe twice. In my lifetime experience over the last 30 years of programming, I've seen these situations 0 times, never. Count the times, count the number of null keyword which happens in your code. And if it's close to this number, close to 35 lines per one null, that's one story. But if it's 2,700 lines per one null, then it's a completely different story. This is good. This is horrible. It basically is everywhere. In Spring Boot framework, in Apache frameworks, in Kafka, in everywhere, in Google frameworks, everywhere. Open their source code and just search, just grab their source code for the null keyword. You will see how often they use it.
The type is the property of the behavior. This is the meta information. It's not a behavior by itself. We didn't ask file or the object X to do anything for us. We just decided what we can do based on the meta information about this object. The object didn't know anything about this situation. The object didn't even have a chance to squeak, didn't have a chance to do anything, to say anything. We just said, your file, then we're going to proceed that way. The object was like, whoops, did you even ask me to do anything for you? No. We don't care what you think. We don't care what you can do for us. We just decide, okay, you're the file, you go left. You're not a file, you go right. That's what here we see happening. And this is reflection. I believe this is very close to reflection, even though a more details-oriented listener would say that it's not really reflection API because, well, it's not part of reflection API, this instance of operator. But I would classify it as reflection in general. On top of the problems which we will discuss today, there is a fundamental problem with reflection is that it makes code analysis very difficult to do. If you try to analyze the code with a static analyzer or IDE or any other tool, the tool will complain. The tool will have problems because the tool doesn't know by looking at your code what exactly is going to happen there. Like with the code before, when we were expecting the object and then deciding whether it's a file or not. If you read this code, you don't know whether the file is coming or not the file is coming. This decision is completely relies on the runtime. But if you use more of the reflection, if you start, for example, making these injections, like dependency injection containers is doing, or you're testing the private method, or you're maybe even injecting some attributes into your class in runtime, then it becomes a total mess for the code analysis tool. So the cost of imprecise reflection handling has increased dramatically. Imprecise. We don't know how to deal with reflection. It's difficult not only for the static analyzer, even for the compiler and for the virtual machine, for example, because it's hard to predict what's going to happen next. It's hard to compile your code because, I mean, it's hard to optimize your code. We can compile it, but we cannot optimize it because it becomes unpredictable, the behavior. I think in general, Java is moving away from object-oriented programming. Every next version of Java is introducing us, is giving us something which is dragging us further and further away from the original idea, further and further away from the concept of object orientation. Java 1, when I was a student, we were using Java 1. And in Java 1, they didn't have a lot of things there. A lot of things. They didn't have generics. They didn't have lambdas. They didn't have uh, annotations. If your design is clean, if your design is easy to understand, if your design is elegant, if your design is object oriented, then fixing performance problems will be smaller task comparing to the task of taking a high performance application and trying to make it design well. That's a completely different story. That's a task which you don't want to deal with that. Yes, maybe this is faster, but how many places in your applications you have where you really care about performance that much? This we are trained, we programmers, we're trained to be obsessed about performance. We're trained to be very peculiar and very cautious about how fast this line of code will work. It's not important. In 99% of cases, it's not important. The speed doesn't matter. With the modern hardware, with the modern mobile phones, we don't care about the performance anymore. Well, we do care, but rarely. And you, in most cases, not gonna face that tasks. The point of object-oriented design is that an abstraction, which is a figure, must be responsible for everything, for instantiating itself, for the behavior, for the encapsulating the data. Everything should stay in one place. When you move away your instantiation mechanism, like the factory method, you lose this cohesion. So you lose the principle of this single responsibility, which you just mentioned. That the single responsibility here means that you are responsible for everything. When you are the figure, then you internally will know how to deal with the method surface. We don't want the user outside of our class to know what's going on inside. We don't want the user to understand that we actually are delegating the calls to different classes. We don't want the user to understand that we have triangle, we have square, and we have polygon. We want the user to deal with just the figure, the most comfortable way. And everything else we just encapsulate. The key point here, I think, is that we should not know what's going on. We must be able to accept the derived, they say base classes here. If this is the figure, then this is I use UML notation. Wait a second. And then the circle. This is the base class, and this is the derived. Derived. Remember, Barbara Liskov said type and subtype. Now we have base and derived. The meaning is the same. We must be able to accept a subtype or derived class. That's very good. Without this principle, it would be very hard or impossible to design anything meaningful because we would have always concrete classes. We would have always it would be difficult to model the reality, the real world, because the whole point of object-oriented modeling and designing is to represent what we have in the real world, represent here in Java, for example, or in C#, represent the things which resemble what's going on outside. And outside, we have the idea of subtyping. We have the idea of categorizing. We have categories. For example, we have animals. And all animals, they have certain properties. And the dog and the cat, they both belong to the category of animals. And then we have category users. And Jeffrey and Sarah and Monica, they all belong to the category users. And that would be difficult or weird or impossible to say, no, we don't have categories. Monica is Monica and Jeffrey is Jeffrey. It's just they have nothing in common. They just, every single individual, every single object is a new story.
we just start from scratch. Monica has a name and Jeffrey has a name. Monica has a salary and Jeffrey has a salary, but that's different things completely. We treat them individually. That would be impossible to design such a software, because you would have to have a payment calculation system for Monica and then payment calculation system for Jeffrey. That would be just weird, right? That's why we say it's a category. We put them all into one group and call them users or employees. And then all of them, all the employees, they have salary. And then that's it. That's why we need types and subtypes. And that's why the system which calculates the salary should not care much about who is coming, who is next, Monica or Jeffrey. It doesn't matter, because they both have salary. I can ask, what's your salary? And I can ask, what's your salary? They're going to give me the different responses, of course, but the way of communicating is going to be the same. This is how subtyping is implemented in Java. Let's get practical now. We have interface figure, and the figure have the surface or the area. You can put the area here, something like that. And then in the interface circle extends the interface figure. This is the category, right? We can call it category or interface. And then the circle is the circle belongs, or actually all circles belongs to the category figures. But we call it figure and circle, even though there are categories. They're not the particular circle. They're not the particular figure. It's a category figure. It's a category circle. So maybe a more accurate name and more accurate design in Java even would be, instead of saying interface figure, maybe to say category figures. Figures in the plural. That would be, I think, more logical. And then we have interface polygon, which extends also the figure. They both have the surface method, but they have something else. The circle has the perimeter, and the polygon has the number of sides. This is something extra. Like with Monica and Jeffrey, for example, Monica works as a designer, and Jeffrey works as a manager. So for the designer, we may have, for example, the model of the computer which the designer uses. For the manager, we don't care about that. The manager have, let's say, all managers, they have the same computers, but designers, they have different computers. So designer has a special quality, special attribute, something different, which is different. Here, the circle has the perimeter, and here the polygon has the sides. Two extra, well, they have something extra, which is different. These are the difference between them. That's subtyping. The circle is a subtype of figure. That's perfect. Everything is fine here. You may say that this is inheritance, and this lecture is that inheritance is evil. That is wrong to have inheritance in object-oriented programming. This is not inheritance. This is subtyping. It's different. We will get to inheritance, and you will see the difference. But now we're talking about subtyping. Subtyping is perfect. We need it. And we need long hierarchies of those types. And that's good if you have very sophisticated, complex hierarchy of types. Not of classes. That's a big difference. Classes and types. Well, in Java, we don't have types, we have interfaces. So interface and class is completely two different things. Interfaces are perfect. Have them many. Make sure that you design those interfaces, that you think about how to allocate them, who is a subtype of what, how many of them. Make them very precise. It's very good that if in your application you have many types, it's just an indicator of a good design. Types, not classes. Another type of polymorphism, which is also a good idea in general, is the polymorphism through generics. You probably know who are these guys, the generics. It's when, let's say, on the take a look at the left snippet, we have stack of strings, we have stack of integers, and then in order to create a stack of strings, we use this class, and then we use this class for the stack of integers. They have the same functionality, but this is how we were designing in Java 1.2.
That was the life of Java 1.2. And then they introduced generics. Now I can say I just have stack, and then this is the type which I pass there. And what happens when I write it like this, then basically the compiler understands that, you mean this, then this is what's going to be placed there instead of this code. It's just a feature for compiler. The compiler reads this and say, oh, we have a good template, because in C++ they're called templates, not even classes, they're templates. In Java it's generics. In some other languages they have something else. But this is basically a template for a class. A template which is generated in compile time, which is used in compile time. When the code is being compiled, the compiler finds this and say, oh, you're going to use stack with a string. Then we just take the template, put the string there, and boom, we have a new class. It just basically saves space. You can live easily without generics, but you will have code duplication. You will have stack for strings, stack for integers, stack for this, stack for that. You're going to have many, many files, which you don't want to have. Any features in the language which belongs to polymorphism, you must use it. It's perfect because it makes code more less concrete. Less concrete means less coupled. When your piece of code expects figure to come, and then the circle can come, the rectangle can come, anything. That means that you in your code don't care much about the specifics of what's going to come to you as an argument. And the less you know about the specifics, the more decoupled you are from those specifics. That means you can design your functionality freely, with more freedom in mind, with more not opportunities, but more, I would say, flexibility of what you can do, because you are restricted by less things. You don't need to know that this is going to be a rectangle or it's going to be a circle. You know less, which is better. And the polymorphism gives you exactly that. It just tells you that don't care about what will be given to you. We will take care of that. You just need to know all you need to know. You need to know. You know what you need to know, that this is going to be a figure, and the figure has a perimeter, for example. Everything else you don't need to know. So we are reducing the amount of strings attached between me as a provider of something and you as a consumer of that stuff. The less we know about each other, and we discussed that in the previous lectures, that the less objects know about each other, the better. And polymorphism is what you get, gives you that. And a little bit of philosophy here. Inheriting, in general, inheritance means receive something. You inherit from somebody who dies, then you get the property from them. That's what the word inheriting is for. Subtyping is subtype and subtype. Inheritance is when you take something which is from the dead person and you put it into your own pocket. So the question is here, who is dead? And I can tell you who is dead. The object is dead if it allows other objects to inherit its encapsulated code and data. So if your class which you design will allow other classes to inherit from it, you killing your class, you make it dead. Now this class is the provider of functions and methods and data to their inheritors, who don't care about it anymore. They will just take the functionality. They will just expect that functionality to stay put, to don't change. Because I take it, I need it this way. Don't change your functionality. And from now, you're dead. You cannot move. You cannot develop. You cannot evolve. Because somebody expects you to be the way you've been last year. So your class dies. and you become a dead element in the hierarchy of classes. You stay there and don't move. This is what Alan Holb said 20 years ago, and I just interpret his words and telling you don't use implementation inheritance. Just forget this feature. This is the evil feature in Java. That was a wrong idea to have it in Java, and it's a wrong idea to use it in Java or any other programming language. You never, never inherit anything from anyone. Only subtyping. Or if you want something to reuse, you go for composition over inheritance. It's a very popular term. You want the square functionality to be reused in the circle functionality. This is how we did it before. You've seen that code already just a minute ago. This is how you do with the composition. You make your class final. The square is final. The circle is final. This is the main things you must have. All your classes must be final. Just make it as a rule for yourself. Always. If you design the class and this class is not final, stop it. You're making the mistake. That's it. No exceptions, zero exceptions. In my applications, I never ever have classes which are not final. Sometimes I have classes which are abstract. Yes, this happens very rarely, but that's a little bit different story. About this we can discuss separately. But if your class is not abstract, then it must be final. In a few words, when your class is base and I inherit from this class, and here you have some functionality where one method depends on another method, then I inherit from this class and I override one of those methods. And then I call the first method. This one calls that one, which is overwritten by the child class. And now the first method just breaks because I basically shoot it in the foot because I have an ability to do that. In order to avoid that, you follow this rule, always final or abstract.